All right, here we are with our second video for Chapter 7, looking at Section 7.2, Sample Proportions. So we've established all of our concepts that we need to be focused on for this chapter, and now we're going to get into specifically how to deal with sample proportions. So in this section, we're going to find the mean and standard deviation of a sampling distribution for proportion. We're going to check the 10% condition before calculating the standard deviation of the sample proportions. We're also going to determine if it's approximately normal, and if it's normal, we're going to calculate probabilities involving sample proportions. So really, we're kind of taking things that we already know and applying them to the concepts that we developed in section 7.1. So when we talk about the sampling distribution of p hat, that tells you that what you're looking at is a proportion. And when you deal with proportions, you know you're dealing with categorical outcomes. So you're dealing with categorical variables. So when you ask a question, that has to be like a word answer, like do you have red hair? Did you pass the test? Things like that. So it says, how good is a statistic p hat as an estimate of the parameter p? The sampling distribution in p hat answers this question. Consider the approximate sampling distribution generated by a simulation in which SRSs of Reese's Pieces are drawn from a population whose proportion of orange candies is either 0.45 or 0.15. What did you notice about the shape, center, and spread of each? Well, if we look at this one here, the one on the left, we have sample size 15, and we have 400 samples. Now, what we see down here, this 0.45, that's the proportion that we're referencing here. And you see that it is close to the true proportion, and it's fairly spread out there. Now, if we were to increase the sample size from 25 to 50, you'll notice that you still are centered at the true proportion, so they're both unbiased estimators, but the one on the right, where sample size was 50, it's much less spread out. And if you're not sure, if you can't see that, you have to take a look at notice the scale. The scale is different. The scale is more zoomed in the one on the right there. You could also look at the standard deviation. On the left side, when sample size is 25, standard deviation was 0.103. When the sample size goes up to 50, now the standard deviation goes down to 0.068. So that's important to note there. Again, just emphasizing the idea that when the sample size goes up, standard deviation goes down. Now, if we were to change it to a p-value of 0.15, here are the same two ideas now. We look at the one on the left, now the standard deviation is 0.071, and on the right it's 0.048. So that's also interesting to note there. When we had a p that was close to 0.5, the standard deviation was larger than it is here when we have the standard deviation at, if we have the p at 0.15. So that's an important thing to note as well. Standard deviation is larger if you have smaller sample sizes, but it's also larger if your p-value is closer to 0.5. Obviously, there has to be a reason to go along with that. Now, getting into the general idea here, when we talk about shape, regardless of the situation, they all appear to be roughly symmetric, and you might even argue approximately normal, but we'll need to check that to make sure that that's the case, because that depends on whether the n and the p are at least 10 and n times 1 minus p are at least 10, again, from last chapter. As far as the center, well, we assume these sampling distributions to be unbiased, therefore the mean of p hat is p. And the standard deviation, well, we know that for a specific value of p, the standard deviation sigma sub p hat gets smaller as n gets larger, but it also depends on the value of n and p. Now, before we get too far, before we get ahead of ourselves here, let's make sure we understand this idea of p hat. P hat is the count of successes in the sample divided by the sample size. So if we have a sample of size 20, and in that sample 11 people passed the test, then the p hat is 11 out of 20, or 0.55. So that's just make sure you understand where that p hat is coming from. Now, we've already established if the distribution is binomial, then the mean is n times p, and the standard deviation is the square root of n times p times 1 minus p. Now, it says since p hat is x over n, that's the same thing as 1 over n times x. We're just multiplying the random variable x times the constant 1 over n to get the random variable p hat. So what that tells you is that we can use these binomial rules to develop this mean as 1 over n times p, or p. But more importantly, it gives us a standard deviation rule here. All we're doing once again is we're just multiplying by 1 over n, and we get this formula here for the standard deviation of a sampling distribution for proportion as square root of p times 1 minus p over n. And from the formula, you can see that as the sample size increases, the spread decreases. This formula is on your formula sheet, so it's not something you have to memorize, but obviously you'll need to know how to use it. So when we talk about the sampling distribution of a sample proportion, we talk about the shape, center, and spread. The mean of p hat is p. The standard deviation of p hat is square root of p times 1 minus p over n. Again, as long as the 10% condition is met, meaning that the population must be at least 10 times the sample size. And as n increases, the sampling distribution becomes approximately normal. But in order for that to be true, n times p has to be at least 10, and n times 1 minus p has to be at least 10 as well. So the general idea, we could have a whole bunch of samples of size n, and we get different p hats each time. But when we take all of those, they are going to be approximately normal as long as our conditions are met, and they can follow this shape with center at p hat and the standard deviation square root of p times 1 minus p over n. So that's it. Again, you see not much really new here other than the fact that we have our new check for the standard deviation of a sample proportion. But everything else is really just an application of things that we already know. That's it for this section. Lots of practice coming up, and that's it for today. See you next time.